So, in the last class we had considered the backpropagation algorithm derivation from a mathematical point of view, and today we are going to see some of the practical aspects of backpropagation algorithm. All right. Now, you have seen in the last class that the local gradient that we are having, for the output as well as for the hidden layer neurons, that local gradient is very much dependent upon the derivative of the activation function, because it is proportional to phi dash of Vj. So, this necessarily means that phi dash Vj should be computable. That means to say that one of the fundamental conditions that we are imposing for backpropagation algorithm to work is that the activation functions that we considered must be continuous and they should be differentiable. Okay. Unless we have that, the backpropagation algorithm cannot work, because in such cases phi dash Vj will simply become undefined. Phi dash Vj will not exist if that is not the case. Okay. So, coming to the question of activation functions to be used in the backpropagation algorithm, certainly the activation functions like McCulloch and Pitts model, okay, or the signum function, they are ruled out, okay, because they are necessarily becoming discontinuous function. Okay. At the point v is equal to 0, the function becomes discontinuous if we are considering any one of those kind of functions. So, instead we should again concentrate our attention to the continuous activation functions, for which the typical examples that we considered were the sigmoidal nonlinear functions. Okay. And for sigmoidal functions, okay, the two kind of models that we are taking are the logistic sigmoidal function and the tan hyperbolic sigmoidal function. Logistic is in the range of 0 to 1, whereas the tan hyperbolic is in the range of -1 to +1, right. So, let us consider first the case of logistic activation function, and we will derive that what is the local gradient that we can compute considering a logistic function, right. And then we will go over to some of the other practical considerations, like what is the effect, like every time we are presenting any neural network algorithm, we have to debate upon the point that what should be the right kind of choice for the etas, that is the learning rate. Okay. We have been telling about compromise, that it shouldn't be too large, it shouldn't be too high, but some research efforts were put in during the late 80s, whereby one can make the algorithm stable as well as cause quicker convergence for it, right. So, that is that will be discussed immediately thereafter, and then we will try to compare about the two modes of learning, that is the batch mode and the and what you can call as the sequential mode of learning, okay, for the case of backpropagation. So, these are the things which I intend to cover in today's class. So, let me first consider the activation functions for backpropagation network, okay, in which I am going to consider the example of the sigmoidal function and especially the logistic function. Okay. So, we consider that as the phi function, we have the logistic function defined as follows. Since we are considering the neuron J, so for the neuron J, the logistic function phi of J as a function of Vjn, okay, is going to be 1 by 1 plus exponential to the power minus a times Vj of n, where you know that as before a is controlling the slope of the activation function, and Vjn is nothing but the induced local field, that is a summation of the inputs times the weight. I mean weighted summation of all the inputs will be the Vj. Okay. So, the definition remains the same only. In this case, certainly the conditions that we are imposing is that a is greater than 0 and Vj that we are considering, okay, can be anywhere in the range of minus infinity to plus infinity. Okay. We are not putting any restriction on the bounds of Vj in this case. Okay. Now, I mean if we consider a logistic function like this, in that case we can take the derivative of this logistic function. So, let us compute this phi dash j Vjn, which means to say that what we have to do is to take the derivative of this function with respect to Vj. Okay. So, that is going to be fairly simple and easy enough. Okay. What will happen is that the denominator term will now become a squared term, right. The denominator will become a squared term, and in the numerator we will be getting the differential of the denominator term and then the numerator term, which is 1 product of that. So, that means to say that the differential of this term only will be there, which means to say that we are going to get the derivative as a times exponential to the power minus a Vj n, okay, by 1 plus exponential to the power minus a Vj n, okay, this term square, right. So, this is going to be the derivative. In fact, this phi j that we are writing can also be written as yj, because that is going to be the net output. So, if this is yj, in that case 1 minus yj, if we consider 1 minus yj will become exponential to the power this term by 1 plus exponential or 1 plus exponential of this term whole square. No, I mean 1 by 1, that is exponential of this by this. So, that is going to be 1 minus yj. In fact, this whole thing could be expressed as a times yj n multiplied by, so this also is yj n. So, a times yj n times 1 minus yj n. All right. So, this is going to be our equation number 1. So, this is phi dash j Vj of n, which is equal to this. So, this we are calling as equation number 1 for today, right. So, now for a neuron that is located in the output layer, okay. So, if neuron j is in output layer, in that case we can simply write that yj n is equal to oj of n, okay. Oj of n being the output, okay. So, yj is the final output, and in that case the local gradient, that is delta j n, will be equal to what? Ej times phi dash j n, right. So, this is Ej at iteration n times phi dash j Vj n, and what is phi dash n if we are considering the logistic function? Yeah. So, first of all, that Ej n could be expressed as simply dj n minus yj n, that is right. So, it is dj n minus yj n, that is going to be Ej n, not yj n, because we are considering yj n to be the output only. So, which is oj n. So, it is dj n minus oj n times, it will be yj n into 1 minus yjn. I mean, that is what we had already derived. So, this is going to be, instead of yj, oj we can write. So, it is ojn into 1 minus ojn. Please verify. Is it correct? So, this is the phi dash j term, okay, that we are writing. In fact, phi dash j will be a times ojn into 1 minus ojn, okay, and ejn is going to be dj minus ojn, right. So, this is, I mean, what we have got is the correct expression for delta jn, that is the local gradient. And if j is a hidden layer neuron, in such case, what will be the expression for our delta jn? Delta jn will be equal to what? Remember our discussion from the last class? Phi jn or phi dash jn, phi dash jn multiplied by summation of what? Summation of all the delta terms, the weighted summation of the delta terms in the output layer, and that weighted summation will be over k, where k is the output layer neurons. So, k is the index for output neuron. So, what we are going to have is phi dash j, that means to say this neuron j which is under consideration vjn, okay, times summation of delta kn w kj, that is correct, delta kn w kjn, and this summation is over k. Okay. Simply what we can substitute is that instead of phi dash j vjn, we can write it as a multiplied by, in this case yjn only we have to write, right. We cannot write ojn because ojn is the output, okay. But in this case yjn will be the output of the jth neuron, I mean the hidden neuron. So, we have to write here yjn only into 1 minus yjn. So, that is the term that we are writing in place of the derivative of the activation function, and the summation of the weighted summation of all the local gradients at the output will remain as before. That means to say that it will be summation of delta kn w kjn, where it is summed up over k, and this is for the case of hidden layer neuron, okay. Whereas for the case of I mean output layer, this is the expression that we have got. This is for the output layer, okay, whereas this is for the hidden layer. All right. Anybody having any doubts or confusion pertaining to this? No. All right. So, now let us look at this, that I mean after all we have derived our expression for phi dash j in, okay, phi dash j. So, let us have a look at this expression, okay. In fact, we have computed phi dash, and phi dash in turn is controlling our delta j, that is the local gradient. Now, first of all, that what is going to be the range of yj according to this activation function? Can anybody say? What is the range of yj? Plus 1 to minus 1, everybody agrees? 0 to plus 1, 0 to 1 it is, okay. Because you see that, I mean, it's very easy to see that, I mean, you don't have to remember it. I mean, even if you just simply have a look at this expression, you can see that what is the bounds on this term. I mean, Vj could be minus infinity to plus infinity, as I said. Now, if I consider the case of Vjn tending to minus infinity, then it is exponential to the power infinite, okay, which means to say that the denominator term is becoming infinite. So, it is 0, yjn is equal to 0, whereas the other extreme is when Vj becomes infinity, okay, tends to infinity. In that case, it is exponential to the power minus infinity, which means to say that this term is 0, this exponential term is 0. So, it is 1 at the output. So, here I mean the way we have written the formula, okay, our yj, I mean that is to say considering this kind of a logistic function, okay, our yj's bound is going to be in the range of 0 and 1. Okay. So, certainly you all agree about the bounds of yj. Now, if I ask you that you try to plot, I mean consider this expression 1, okay, and try to find out that how this phi dash j function changes with the yj. Definitely phi dash j is dependent upon yj. So, how is it dependent? Where are we going to have the maximum value of phi dash j? 1 by 2, yes. That means to say that when yj is equal to 0.5, okay, in that case we are going to get the maximum value of phi dash j. And what is the value of phi dash j when yj is equal to 1? 0. Simply substitute here, it is 0. What happens when you take yj equal to 0? Then also it is 0. So, that means to say that for yj equal to 1 or for yj equal to 0, this equation 1 gives us a value of 0 for the derivative. So, that means to say that in those places the derivative of the activation function becomes 0, and when we have yj is equal to 0.5, that means to say that exactly at the mid range of y, there we are going to have the value of phi dash vj to be the maximum, right. I mean you can simply differentiate this phi dash j with respect to yj and see it yourself. I mean by equating the derivative to 0, you can find out the point of maximum is certainly becoming at yjn is equal to 0.5. So, that means to say that the phi dash vj is definitely being maximum at the mid range of y. That means to say that the weight adjustments that we are going to do, that is to say ultimately we are going to do a delta wji based on this computation, isn't it, based on phi dash j or based on the delta j, okay, we are going to find out the delta wkj, okay, and that weight changes, I mean those weight changes will be maximum when we have yjn equal to 0.5, or rather to say at the mid range of the output values the weight adjustment is becoming maximum. In fact, this is one thing about it, okay, which I mean definitely adds to the stability of using such kind of logistic functions in the back propagation network. Now, very similarly, okay, in a very similar way we can show that instead of taking a logistic function, if I had taken a tan hyperbolic function, okay, I could have derived a very similar expression to that. Okay. Only thing is that there instead of taking 1 by 1 plus exponential to the power minus a vjn, I should have taken tan hyperbolic of a vjn, okay, and then I could have computed a very similar expression. So, I am not going into the computation of that, okay. There should be something that should be left to the students as well as the viewers for them to solve, okay. So, the tan hyperbolic case you can consider and solve it yourself, okay. It will be quite easy following the same lines. You can derive the expressions for phi dash j and correspondingly the delta j, considering j to be the output layer neuron and j to be a hidden layer neuron. So, that is as far as the activation functions considerations are there, okay, which we have now derived out of this, okay. And then the next point to consider is the rate of learning, okay, because in the expression that we had got, okay, as before, I mean remember the expression that we had got in the last class about the change of weight, that is delta Wkj. Delta Wkj is dependent upon what terms? Remember, it is dependent upon eta. So, that is equal to eta times delta J times y. Okay. So, now what we have to do is that definitely, that means to say that it is dependent on eta. Now, I mean, we have been discussing about etas, okay, all the time. In this case, you see that the backpropagation algorithm that we have got in this case is definitely an approximation to the steepest descent problem. I mean, this is also a solution of the steepest descent only, okay, but in this case it is an approximated version of the steepest descent. And approximated version of the steepest descent means that in the case of a perfect steepest descent, we know that, see, ultimately what is it that is happening in the case of the steepest descent algorithm? We start with some value of weight vector, right? So, we are in some m-dimensional space initially, we are in some point in the m-dimensional space, okay, with the initial set of weights, okay, and then we are going to move in the weight space, m-dimensional weight space, and we will follow a trajectory that ultimately takes us to some value of weight which we have been calling so long as the W star vector, okay, and W star vector is something where it gives the minimum value of the cost function that we have been considering, and the trajectory in the case of a steepest descent algorithm is going to be a smooth trajectory. So, since the backpropagation algorithm is an approximation to the steepest descent, okay, certainly the trajectory that we are going to follow out there in the m-dimensional space is not going to be a smooth trajectory, okay. The trajectory is very much dependent upon eta, and as our discussion has gone in the case of the single layer perceptron also, that there is a trade-off that is definitely going to exist. You make eta too small, okay, then what happens is that the learning is getting too small, but the trajectory will be smooth, and you will not run the risk of having a an instability, okay. The system will be always stable, whereas if you are making eta to be too large, okay, then the learning definitely will be faster, but the risk is that we can it can lead to an instability, okay. So, now there were researches, okay, to find out that if there could be any solution to this, that means to say having a faster learning and also a better stability condition, okay, or rather to say a guaranteed stability condition, is that possible? So, now what happens is that in this effort, okay, some researches were done, and as I was telling you that most of the developments in the multi-layer perceptron and so to say about the backpropagation algorithm etc. were done in the 80s, and it was the book by Rumelhart in 1986, the book on parallel distributed processing, which we had mentioned a few classes back. In that book it was presented, okay, that one of the solutions to have both together, that means to say stability as well as faster learning, is to add what is called as a momentum term to the learning. And using the momentum term, which was actually suggested by Rumelhart, okay, there the delta Wji that we are going to have, delta Wji at iteration n, is going to be equal to alpha times delta Wji n minus 1 plus our usual learning term that exists, that means to say eta being the learning rate, times delta Jn, which is the local gradient, times Yin being the input to the neuron J. So, here this term is very familiar to us. Okay. This is the normal learning term that we always have, whereas this is something which is new to us. We haven't come across this term earlier. So, this is an addition, and just see that here what is the significance of that. That means to say that the change of weight that you are doing is in some way proportional to the change of weight that you had done in the earlier iteration. Okay. That means to say in the n minus 1th iteration, whatever delta Wji you had considered, you are taking a proportion of that, okay, to be added up. So, in this case alpha is going to be a constant. Okay. In fact, alpha is normally taken to be a positive number, okay, and alpha is referred to as the momentum constant. Momentum constant. In fact, why is it called a momentum? I mean, if you spend a bit of time on it, okay, I think it is very easy to understand. That means to say that over and above your normal learning, okay, you can afford to have eta to be small, because we know that eta small is good from the stability consideration. So, despite having small eta, okay, we can have a quicker learning, as if to say giving it a push. Okay. Giving it a push, that means to say that applying an external force, and force, as we know, okay, will be causing a momentum. So, definitely there is every reason to call it as a momentum term. So, which is added to this delta Wji. Now, this in fact, I mean this equation that we have got over here could be written in terms of this, that delta Wjin, I mean in the form of a difference equation. If we write, then we have to write it as delta Wjin minus delta minus alpha times delta Wji n minus 1, which should be equal to eta times delta Jn Yjn. Okay. Which means to say that very similarly we are going to have delta Wji n minus 1 minus alpha times delta Wji n minus 2 is equal to eta times delta J n minus 1 Yj n minus 1, isn't it? I mean, if we had written the same expression for the earlier iteration, the difference equation for earlier iteration would have been like this. So, which means to say that if somebody tells me, I mean like this we can go on, isn't it? I mean like this we can go on for n minus 2, n minus 3 and so on up to, I mean up to n minus n, that is Wgi 0, which means to say the initial. We can go there, and if we have to eliminate all these intermediate terms, let us say that if we have to eliminate this delta Wgi n minus 1 term, simply what we have to do is to multiply the second equation, okay, by alpha, isn't it? So, if I multiply this whole equation, this second equation by alpha, then what I am getting is alpha times delta Wgi minus, here it becomes alpha square. Okay. So, if I add up these two on the left hand side, it is delta Wgi n minus alpha square times delta Wgi n minus 2, which is going to be equal to eta delta j n yj n plus alpha times eta delta j n minus 1 into yj n minus 1. We can shift the delta Wgi term on the delta Wgi n minus 2 term on the right hand side. From left hand side we can take it to the right hand side, and in that case delta Wgi n will become alpha square delta Wgi n minus 2, okay, plus it is going to be eta times delta j n, okay, y j n, here it is going to be eta alpha, okay, plus eta alpha this term. In fact, if we keep on doing it, then I mean here we have expressed it in terms of n minus 2, but ultimately if we add up everything, n minus 2, n minus 3, n minus 4 and all that, in that case the delta j I n is going to be expressible as a time series. Okay. So, we can, I mean you can verify this yourself by proceeding with the difference equation solving approach, that we are ultimately going to get delta w j I n to be equal to eta times summation t is equal to 0 to n alpha to the power n minus t into delta j t times y I t. Okay. This is something that is going to express it. Eta is a constant, okay. Eta is not varying with iteration. Alpha is also a constant, but here why I had to put alpha term inside the summation is because it is alpha to the power n minus something, okay, n minus t, and in this case t is the quantity that is changing. That means to say that considering t is equal to n, okay, it is alpha to the power 0, so it is delta j n, eta delta j n y I n, the first term. Then t is equal to n minus 1, I mean if you look at it from a reverse way, t is equal to n minus 1 means it is alpha to the power 1, delta j n minus 1, y I n minus 1, the term that we were writing out here, okay, for the second equation. And like this it is a summation series that is ultimately going to be. So, this is a time series representation of delta w j I n, okay. Okay, so this is a time series. So, this is a time series representation, and what is the length of the time series? Length of time series is in this case n plus 1. Okay. Now, simply what we can do is that we already know that delta j times y I is going to be equal to the negative of dou E dou w j I. Okay. I mean, isn't it the rate of change of the error function with respect to, I mean error with respect to, I mean the cost function with respect to the change of weight. So, I can express this same equation as delta w j I n equal to minus eta times summation t is equal to 0 to n alpha to the power n minus t into dou E t dou w j I t. Okay. So, this is going to be our series representation. Okay. Now, we can spend a little bit of time on it and find out about the convergence aspect of this equation. You see, we are considering the alpha to be a positive quantity, right. Now, the thing is that we can take, I mean we never said that we have to put the alpha term to be a, I mean alpha term is greater than 1 or alpha term is less than 1, that one we haven't really specified. So, firstly that here we have to know, I mean one consideration which should be there for us is that the alpha term that we have to take should be definitely within 0 and 1, okay, because one thing is there that you can make out from this series itself, that if I put alpha to be greater than 1, then delta w j I term will be uncontrollable. I mean, it will increase because as the power of alpha increases, if alpha is greater than 1, then the contribution of these terms which are getting summed up will increase, and definitely that will be uncontrollable. So, that is not the not something that we are looking for in this case. So, definitely we restrict the range of alpha to be this, that within 0 and 1. Now, if it is within 0 and 1, then one thing is very sure, that this expression that we are getting, okay, alpha to the power n minus t into dou E dou Wji, okay, this is surely going to be a convergent series, okay, because with I mean alpha less than 1, I mean modulus of alpha being less than 1, it is going to be convergent, and there is some consideration that we can have on this dou E dou Wji term. Now, this term definitely we are having n plus 1 such terms, is not it, and they are getting added up with the value of this alpha to the power n minus t. Now, if it so happens, now alpha is positive in this case, okay. Now, in this case, if this dou E dou Wji is having the same sign in every iteration, for every t, if it is having the same sign, in that case the modulus of delta Wji is going to be a higher value, is not it? I mean, although it will be convergent, but modulus of delta Wji, okay, grows in magnitude. So, I can say that if dou E dou Wji, okay, has the same sign for all t, then the modulus of delta Wji, okay, that grows in magnitude, correct? Look at this expression to confirm this. Every dou E term is having the same magnitude. So, either it is increasing in the positive direction or it is increasing in the negative direction. There is a summation term that is existing, right. So, grows in magnitude, delta Wgi growing in magnitude means what? That it refers to an accelerated descent, okay. So, it is an accelerated descent. It is descent, no doubt, okay. It is following a steepest descent, but in an accelerated way, okay. We are coming down after somebody has given us a push. So, we are coming down little faster, okay. And the other thing could be, the other extreme could be that dou E dou Wgi is alternating its sign with every iteration. What happens in that case? In that case, if dou E dou Wgi is alternating its sign with every iteration, then mod of delta Wgi is going to be small in magnitude, is not it? Because one term is tending to add up in the positive direction, the next term is going to subtract it in the negative direction, okay. So, addition subtraction, okay, continuously happening. So, that restricts the mod of delta Wgi. Now, if it is something in between, okay, that means to say that few terms are having same sign, few terms are going to have opposite signs, okay, that means to say that it will be within these two extremes, but one of the extremes is going in the form of an accelerated descent, and the other extreme is that if dou E dou Wji, okay, alternates its sign in every iteration. In that case, delta Wji mod of that, okay, is small in magnitude, and this certainly has got a more stabilizing effect. Okay. So, what we have got as the momentum term is not something which is risky in that sense, okay. Even if it is an accelerated descent, but still you remember here that because alpha is restricted within 0 and 1, okay, we are not going to have an unbounded increase of delta Wji. Okay. So, definitely it is stable. So, with stability it is possible for us to have an accelerated descent. Okay. That of course depends on what your derivative of this E term is with respect to Wji. Okay. And the other possibility is that it is small in magnitude, and if it is small in magnitude, then I mean definitely it stabilizes. Now, the momentum term has got two effects. Not only can it contribute to faster learning, as we have just now shown, that means to say that possibility of some form of an accelerated descent. It also helps in avoiding the local minimum, because one thing is there, you know, that I mean again going back to our original discussion, that the back propagation algorithm is an approximation to the steepest descent, and in a steepest descent, okay, the convergence to a local minimum is guaranteed. Convergence to a minimum in fact is guaranteed, but whether that is a local minimum or global minimum is not very clear to us, because if the surface, if the cost function surface in the multidimensional space is such that it could be having local minimum as well as global minimum, then at least the steepest descent can bring us to a local minima and trap the solution in that manner. Whereas in the case of, in this case, if we are adding a momentum term, okay, the momentum term has got some effect in avoiding the local minimum. In fact, more on the avoidance of local minimum we are going to see when we discuss about the aspects of simulated annealing. Okay. Any doubts that you are having related to the learning rate aspect, what we have just now presented in terms of its momentum parameter? Any queries related to this? Yes, please.
So in this algorithm, first we are propagating to the output node.
First we are propagating our
With
right,
propagation.
right, right.
So you are saying that after each back propagation we are doing with iterations.
After every back propagation, yes. I mean we are first doing a forward pass, then we are doing a backward pass, and the backward pass is allowing us to calculate all the delta j's, and then after calculating the delta j's, we are calculating the delta wji. So only thing that we have modified is that the algorithm that we have been talking so long is as if taking alpha is equal to 0. In this case, you just substitute alpha is equal to 0, then it leads to the unmodified back propagation algorithm. That means to say unmodified weight updating. Okay. In this case, what we have simply done is that instead of doing the weight modification simply according to eta delta ji yi, we are adding a momentum term to it. So that we are doing after the backward pass is done. Okay. That is only during the change of weight delta wji that we are introducing this term. That certainly does not affect our forward pass or the backward pass.
So we are at each back pass, we are doing at each even node, we are doing this number of iterations.
At output node as well as the hidden nodes, we are doing the delta j computations.
So it will take lots of time for system to stabilize.
You see, this delta wji that we are doing it connection by connection. That means to say that when the forward pass is done and then the backward pass is also completed, okay, I mean we are, I mean, when we are completing one of the nodes, then we are computing its corresponding change of weights. We go to another node, compute its change of weights. Okay. So, we update the weight as we go from one layer to another, I mean starting with the output layer to the next layer to the next layer, like that. As we go on, we will update the weights every time. Okay. So, we have to allow for that much of computation, but certainly since we are doing this computation, I mean certainly does not add to anything like instability or anything like that. Okay. We are just taking this time. I mean there is nothing different from the original backpropagation algorithm, except for the fact that computationally you are introducing one more momentum term, that is all. Any other doubts?
When you calculate the generalization of delta Wjn, sir, that step I can follow. You have shown one example for n minus 2 and then you have given alpha square term comes. And generalize that equation. I just missed that step. How
you see, I mean that is just to show you some steps about this. Yeah. So, this one, right?
After this, sir. After this, yes, sir. From this you have gone to
Yeah. So, this is the difference equation involving n and n minus 1. Likewise, I can have a difference equation involving n minus 1 and n minus 2. Okay. So, which is going to be what? Alpha times this minus alpha squared times this, okay, is equal to alpha times this. Okay. So, now if I add up these two, then what happens? Then if I simply add up, then we are getting delta Wgi is equal to alpha squared times this plus this term. Okay.
after this you have generalized it, that step I can follow.
Okay. After this, yeah, this is I'll tell you here what you are getting is delta I mean alpha eta delta j n minus 1 yj n minus 1, all right. So, you see that this is for two terms that I have got. That means to say that if I had got this for three terms, then what would have been the case? Then it would have been delta Wgin equal to alpha cube of delta Wji n minus 3 plus eta terms this, alpha into eta terms this, plus alpha square into eta terms of this. Now, that means to say that ultimately you reach what? Alpha to the power n delta Wgi 0. And what is delta Wgi 0? It is 0. So, this term ultimately does not remain. What remains is the next term, that is to say eta delta jyj plus alpha eta delta jyj plus alpha square eta delta jyj plus alpha cube eta delta jyj, like that it goes on, and we have to sum up all these things together, okay, and that is exactly what we have represented in the form of this time series. Is it clear to those who had any difficulty in following this? All right. So, this is about some form of an accelerated learning using the momentum term, okay. And now, there is one more debate that we should initiate, that is to say that whether the sequential learning is good or the batch mode of learning is good, right. Now, the discussion that we have been having so long is as if to say that we are presenting one pattern which we are calling as by the index n. That means to say that when we are putting everything within bracket n, means that it is the nth iteration, or rather the nth pattern, as if to say that we are presenting one pattern and then we are adjusting all the weights, and then we are presenting the next pattern, adjusting all the weights, and so on. Followed. We will be given, okay, a training set. A training sample is something that we begin with. That means to say that we will be having a set of D and a set of xi's, okay, where xi's are going to be the input vector, okay, and d, or rather to say di, is going to be the desired output. Okay. In fact, in this case I can say it is di in the form of a vector also, okay, meaning that since the output is going to be from several neurons, I can describe it in the form of a vector. So, I am feeding one pattern, calculating its errors, okay, at the outputs, and then making the readjustment of the weights, then only feeding the next pattern. Okay. That is the approach that we have been following, and this is called as the sequential mode of training. This is sequential mode of training. Now, as we discussed last time, that we definitely have a fixed set of patterns, fixed set of training patterns, right? And once the system goes through the training of one set of training patterns, the complete set of training patterns, when that is completed, we are calling that that is one epoch of learning is over. Okay. And then what we are doing is that we are, can we stop the network there? Certainly not, because this is only once we have gone through all the set of patterns. Now, we are going to repeat that epoch again. Repeat that epoch means that again start with the first pattern, second pattern, third pattern. With every pattern feeding, you update the weight, okay, feed the next pattern, like that it goes on. So, again we will be completing the second epoch, then we will be completing the third epoch, and so on. Okay. Now, where to stop, that is also a question that we should answer. Okay. What should be the stopping criteria? But coming to the question of the sequential mode of training, we are doing epoch by epoch. Now, one thing which you could have done in an alternative way is that instead of adjusting the weights at every iteration, okay, if we could adjust the weight, okay, once all the epochs are once all the patterns in the epochs are presented, then adjust the weight only once. In that case, the difference would have been that you could not have, in this case, in the case of sequential mode of training, what is the cost function that you are taking? It is simply the instantaneous value of the error energy. It is simply the instantaneous value of the error energy that we were considering for a sequential mode of training. And for a batch mode of training, what we would have considered? Simply the E average. E average that we had discussed few classes back, that would have been our cost function, which means to say that after computing E average, we should have taken the gradient of that E average and then would have adjusted the weights according to that. Even that way also we can derive a back propagation algorithm. So, there what happens is that the weights will be updated based on that E average once for all. That means to say once per epoch it will be adjusted. Alright. Now, the debate that one can come to our mind is that whether the sequential mode of training or the one that I described just now, that is to say the batch mode of training, which one of these two is better. Okay. Now, I can ask the students present over here to initiate this kind of a debate. What is in your mind? Let me just hear from one or two of you about your feeling. What one would you prefer? Sequential. Is it a kind of a consensus in this house? Everybody feels sequential. Okay, one good reason, any one good reason for choosing sequential and rejecting the batch mode as such? Huh?
We are training after one epoch.
Yeah.
So if you are recognizing some pattern, you won't be able to differentiate. We are training for each pattern, for each input pattern.
You see, if I try to counter your debate by saying that, okay, you are saying that with every pattern you are learning and you are contributing that incremental learning. Now, whether you incorporate that learning immediately or whether you defer that learning, how does it matter? Because after all, if you are considering E average, okay, that E average also is containing the accumulated errors. Okay. So, I mean, ultimately we are learning, I mean, it is something like this, that whether you read one page and then you try to assess that how much you have read, okay, with every page you do that, okay, update your learning, or other thing is the, I mean, other alternative is that you read the whole chapter, okay, and then only you think that what you have learned, okay. Okay, fine. I mean, I don't have much of a time to continue with this debate in this particular class. So, in the next class, we will continue this debate and find out that between the sequential mode and batch mode, which one are we going to prefer, okay, and under what condition. And the second discussion that we wanted to make is that what should be the stopping criteria for that. Okay. So, that we will do in the next class. Okay. Thank you very much.